as Leonardo said, I'm Xabier Echeberria-Barrio from BComTech. It's a research foundation where we are part of cybersecurity department there. And our publication, our article is Neuralsentinel enhancing a model trustworthiness. This presentation was developed in Kinetics European project in a hackathon to make end users to understand the neural strengths vulnerabilities and how you can face or solve those vulnerabilities of the neural networks. Okay. Okay, so the first things we start with this field more or less 3-4 years ago, where we noticed that that the deep neural networks was starting introducing in several critical fields such as healthcare, automotive, and so on, where the decision making of those models is crucial. And one of the biggest vulnerability was discovered in this field is named evasion attack, and the vulnerability consists in add very little noise in a introduced input, for example, in an image, and with the indistinguishable modification, you can make a misclassification or generate a misclassification in the target model. All this made us start studying about this field, and we start with concretely with evasion attack. So the evasion attack, to introduce evasion attack, you know now in what is evasion attack, but you can generate this noise in different ways. For example, the first one was introduced in 2014 by Goodfellow, and the name of this algorithm is fast gradient sync method. This method calculates the gradient of the neural network's loss function with respect to input data. It makes small adjustments to the input data to in a direction maximizing the loss function, and with these small modifications, these algorithms sometimes obtain the misclassification of the model of the neural network. This was the first one, but for example, Basque iterative method was an improvement of the fast gradient algorithm, because in this case the perturbations are added slowly. I mean, the perturbations are smaller, but you have several steps to add this small perturbation, generating a more effective adversarial example. The next one is also a progressive improvement. In this case, I wouldn't say it is an improvement. It's another taking the beam method is another way to obtain the same thing. Okay, so this project gradient descent method, it takes epsilon side perturbation, and it doesn't take only one direction. It tests all the direction around the point you have to make the perturbation. and because of this, the project gradient descent method is slower, slower than the beam method. Okay, the next one is another type of it generates different noise. It takes well, the name is Jacobian based salient map attack. It was presented in 2016. And in this case, it works by saturating pixels of an image to the maximum or minimum level. In this case, it makes the misinterpretation of the model according to the input data. It achieved to confuse the model with the misinterpretation of the input data. And the final one is deep full algorithm. This is also from 2016. It consists an entirely estimated decision boundary of the neural network, computes the minimum perturbation required to move an input data points across the boundary. Core idea in this case is the other options makes make the modification, the small perturbations, or tries to improve the small perturbations, only focusing on the small perturbation. But in this case, this algorithm at the beginning starts looking how is the behavior of the model and where are those decision boundaries to select, for example, that point, and that point is the point that we have to modify, because it's the point that with less modification we can't misclassify the input data. This is the part of the attacks, evasion attacks. Obviously, there are more evasion attacks, but we decide to select those because we consider that are the most common or most widely known evasion attacks. And now we are coming to defense strategies. The first defense strategy was proposed in 2014. The name is adversarial training, and the idea behind this defense is that, okay, we have adversarial examples. Our model doesn't know how to classify them correctly, so we can understand adversarial examples as data that our model doesn't know. And because of that, the idea of this defense is, okay, let's create those adversarial examples, and let's retrain our model with the adversarial examples. And it works. However, it has a big problem, that the adversarial examples are millions and millions of adversarial examples. Even you can generate new adversarial examples when you are retraining. So in this case, it's proof that it's not really good defense, because every time you are retraining, you are generating a new adversarial examples or possible adversarial examples. The next one is dimensionality reduction. It was presented in 2021. This defense takes as base idea that the adversarial example is no more than add a little bit of noise in the input data. And in neural networks, we already know different structures that are able to, or are capable to filter some noise in the data. For example, autoencoders are a neural network structure that are able to reduce the noise in the input data. So we can take those autoencoder and put them, for example, in some inside of our target model to make more difficult that misclassification, since um, since if an adversary is adding a small perturbation in the images, our autoencoder is able to reduce this small perturbation, even delete this small perturbation, making this possible adversarial attack in the original image. The next defense is prediction similarity. This was presented in 2021. This prediction similarity is more as a detector because it is focused on the detection of the process of adversarial example generation. I mean, when you have to generate an adversarial example, that you need several steps, several tries, or several predictions of the model. For example, you have an image, you can introduce this image in the model, obtaining the prediction. With this prediction, you can compute the noise to a small noise, a small perturbation to add to the input image. You have a new image, and you have to introduce this image in the model, obtaining a new prediction, obtaining a small perturbation, adding to the new image, and so on. This process, if you can notice that in this process the predictions are receiving very similar images. So this prediction similarity consists on detect those processes where, for example, in 50 steps, you have a equal or almost equal image in the as input data. Okay, this process makes the detection, and it had a really good results at the beginning of the when it was developed. Defensive distraction. This defense was presented in 2016. Uh, Basically, it makes a student model using softened probability distribution from the teacher model. Teacher model transfer information about the distribution, resulting in a more generalized and less sensitive network, avoiding this small perturbation because you have now two models to compare and so on. And finally, finally, gradient masking occurs when the gradients of the networks loss function become too small or vanish during the propagation. Problematic for adversarial attack as it hinder obtaining meaningful gradient information for crafting effective perturbations, and mask gradients, making it difficult to attackers to identify sensitive features and perturbation direction. As we mentioned previously, different options to obtain this noise is focusing in the loss function and maximizing this loss function. This maximum is obtained by the gradient, and if you are masking the gradient, you are making this process more difficult. Okay, next part is explainability and interpretability. Those tools was presented. Maybe you hear sometimes that the models are black box. Are black box because you know what are you introducing in the model. You know what is predicting the model, but you don't know why this model is predicting that. Basically, explainability and interpretability tools are tools that try to clarify the behavior of the model and why it's taking or making that decision. One of the typical technique is Shapley, additive, and explainability, in short, SHAP. This technique is based on game theory, attributes, feature contribution globally and locally. Basically, it classify the features, saying which features are the most important to that prediction and which are the less important to that prediction. You can see there the image where the left column are the features, and how the features are sometimes very important and sometimes are with low important. Okay, continuing with local interpretable model agnostic explanation, LIME, in short, LIME. Basically, it explains local explanation for the model predictions, select specific data, introduces small random feature modifications, and evaluates the model on this sample. Captures how features relate to the prediction in the neighborhood of the selected instance. So you have the image how if you can select one feature in this explainability tool, and where is in the map of decision making in the model and which is its relation with the boundary decision. Other tool is attribution techniques for understanding how input feature contribute to the prediction made by deep neural networks. Calculates relative contributions of features across neural network layers and focus on understanding feature contribution through the networks. Basically, it generates different graphs to explain the behavior of the deep neural networks. Other option, other explainability tools is class activation map, in short, CAM. Basically, this is always used with, or several times used with, convolutional network, because convolutional networks convolutional network works with images, and with this type of method you can see where those convolutional networks are focusing on the image. For example, if we want to see if in the image is a dog, you can see right here that the model is focusing in the dog to classify that image. And finally, we have explainability method for neural networks. This explainability tool was presented for us in 2022, and basically it tries to generate a representation of a neural network, but with a representation that show and highlight the behavior of the neural network. The representation is in graph format, with nodes and where nodes are neurons, and the activation are the connection between nodes. With this explainability tool, we were able to detect different behavior or behavior changes in the model when the model is under adversarial example attack or evasion attack. So yes, with all these techniques that we can find in the literature, we decide to generate a first version or a first prototype with some of those method to introduce this defense, this knowledge in the end user. Basically, we have a Neuralsentinel. Neuralsentinel is divided in 3 modules. You have Neuralsentinel module, API-REST module, and visualization module. First of all, you have to decide if you have a model or you have data. You have to select the your neural network. You have to select your data and introduce in the Neuralsentinel prototype. With that, once you introduced this model and this data, you can start testing your or evaluating your model, your own model. How? Okay, first of all, you have Neuralsentinel module. Neuralsentinel module allow use, for example, defenses, attacks, and some explainability tool. Between the attacks nowadays, we have a fast gradient system method, beam method, and a project gradient descent method. These 3 attacks are integrated in the Neuralsentinel. Then we have also 3 possible defenses. We have adversarial training, we have dimensionality reduction, and we have prediction similarity. And finally, we have 2 explainability methods, where are the one we presented in 2022 that I mentioned previously, and another type of information that I'll show you in a few minutes. Okay, once you have all of your model and your data introduced, you can do all these methods, or you can analyze all these methods in your model, but you have to communicate with an API model. This API model contains different functions to let's say call the function you have able in the Neuralsentinel model. And finally, this is the visualization module. The visualization module consists in you can see right here. You can see right here the first step, where you have to decide which model you want to analyze. Once you have the model selected, you have to select if you want to attack, if you want to defend. And sometimes right here in the parameters column, you will have only one parameter, epsilon, because the 3 attacks need epsilon parameter, but sometimes you need also a step parameter, depending the attack you want. And you can attack without defense to see how the attack affects to your model. And you can attack with some defenses to analyze how those defenses protect your model. Basically, for example, this is the first explainability tool, where you can see how the original accuracy is perfect, but with the adversarial attack, you are obtaining a reduction of accuracy. Okay, and those metrics are some metrics to see how far or how different is the created image to the original images. Okay, continuing. This is the last explainability tool, where basically we have this is a monitorization of the neurons in the model when the attack is happening, and you can see how the impact value of different neurons is decreasing and others are increasing. And actually, it explains perfectly how is the model modifying the decision making, because the neurons that are specialized in detect one thing is reducing their impact, and on the other hand, the others that are less important are increasing their impact. And conclusions, our idea is, okay, with this, I told you previously, our idea with this is to extend this knowledge and these vulnerabilities, and and to say that those vulnerabilities are real, and 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 the models needs to be analyzed and evaluated with those type of tools to to make them more robust against any type of attack. Also, I would like to mention that the Kinetics project hackathon was a successfully analyzed an ML assistant to diagnosis cancer from a skin breast image, and was successful with successful results. And future works, the important one, or the one we have on mind, is that we would like to add more methods that we mentioned to you in this presentation. We would like to introduce all those methods in the Neuralsentinel prototype, making this prototype bigger and bigger, making the evaluation better and better, because you can select more and more analysis and more tests. And this is all from my side. Thank you very much. If you have any question, you can contact with me by email, xecheverria@bicomtech.org. And if you have any question, I'm ready to answer you.